This is the first of a series of videos on the science of clouds. Clouds are an important component of weather. They're important for severe storms. They're important for many aspects of weather. And they're also an important component of the climate system. So we're going to use these videos to talk about the processes in which how clouds form, how they affect climate, how they affect weather systems, precipitation, various aspects of clouds that are important for understanding weather and climate. So our first talk is going to be about the science of clouds, on how clouds form. And so we're going to concentrate on that. The first aspect of this is we're going to try to figure out what is a cloud. We have to define this. And we'll point out that water can exist in three phases in the Earth's atmosphere. It can exist as a gas, which we call water vapor, as a liquid, which we call water, as a solid, which we refer to as ice. So it's important to understand that the water vapor is invisible. So in this room, there's water vapor, but we can't see it. In the atmosphere outside, there's water vapor. We cannot see that invisibly with our eyes. We can see it in other ways. But the question is then, what is a cloud? So the cloud, if the water vapor is transformed or transitions into a liquid or a solid, then that is a cloud. And the cloud droplets are what we see when we look at the atmosphere, or look at the atmosphere. So we're going to split these up into two types of clouds. I'm going to call them warm clouds and cold clouds. And the warm clouds are clouds which are basically below freezing. And those clouds are composed of water droplets. And those droplets have dimensions of about 5 to 50 microns. Now that may be kind of hard to visualize, but a human hair can range from 20 to 180. There's a lot of variability in that. But to give you like 20 to 180 microns, to give you an idea. So you can actually see you can usually see the width of a hair. And the same way that if you look closely, you can actually see the water droplets, even though they're fairly small. Now, because they're small, they do not fall very quickly from the atmosphere, so they remain suspended for some time. They do drift down with time, but not at a very rapid rate. So the droplets form from water. The size can vary as the clouds mature. The size can vary even when the droplets form. So those are the warm clouds. Cold clouds, where ice particles, they have ice itself can have many shapes and forms. Here, for example, is just illustrating some photos of some ice crystals. Here's hexagonal plates. These are hexagonal columns, so six-sided columns of ice. This is a more traditional snowflake feature that we see here. And so we can see the different forms that it can take. Now, the ice forms when the water is deposited or the water droplets freeze. So it's a little bit more complicated in terms of how the ice forms. And we're not going to really concentrate on that in these talks. So we're going to concentrate on warm clouds. I should also point out that water droplets can exist at temperatures below freezing, below 0 degrees C. In fact, we call those supercool clouds, and those are in a special category by themselves. So let's look at how these clouds form. We're going to start with the source of the clouds, which is the water vapor. So let's get a little bit of a better understanding of what water vapor is and how it works. So I'm going to take a little container here, and I'm going to have a vacuum in it, and I'm going to have some water in the bottom here. And then as time goes along, some of the water molecules from the surface will evaporate and become water vapor up in this part of the container. So when that happens, the initial pressure is 0 because it's a vacuum, but the pressure will start to increase slowly because of these water molecules that form the water vapor. So we call that the vapor pressure. Well, I designate that with an E here just to kind of keep track of it here. So it's a vapor pressure. So as this goes along, as there starts to be more and more molecules of water vapor, some of those vapor molecules will then condense again on the surface. So there's a process that goes on. So eventually we get to a situation where the vapor pressure is such that the condensation, that's the removal of the water molecules from the surface into the vapor phase, is equal to the condensation part. So this is the evaporation condensation, and those two are equal to each other. We have an equilibrium, and we call that equilibrium that has a certain saturation vapor pressure. We call that E sub S here, just to, again, to kind of keep track of what we're doing here. So we start out initially, nothing. Intermediate, we have the evaporation exceeding the condensation, and over here we have the evaporation equal to the condensation on the surface, and at that point we have an equilibrium. Now, if we warm this water up, we're going to find that the evaporation will start to increase. So I'll show that in the next slide here. So I've warmed the water up here, and in this case now the evaporation is increased again, and so the vapor pressure is going to start to increase relative to what it was at the other water temperature. And eventually, though, we'll reach another equilibrium. And again, this time, we're going to find that the evaporation is equal to the condensation, but the vapor pressure has increased because of this increased temperature. So the saturation vapor pressure increases with temperature. So if we quantify this a little bit more here, saturation vapor pressure increases with temperature. I have a plot here which is showing saturation vapor pressure. Now these units are in millibars. And just to give a perspective on this, the surface pressure from the atmosphere itself is about 1,000 millibars. We don't usually hear that number in weather forecasts or other things, but we also sometimes hear the pressures falling or decreasing. But at the surface, about 1,000 millibars. Now as we go up in the atmosphere, the pressure tends to decrease. If we're in Denver, Colorado, for example, the pressure may go down to 850 millibars because we're at higher elevation. So as we go up in the atmosphere, the pressure decreases. But back to the point here of the saturation vapor pressure, this is where we have that equilibrium inside the volume. We see as the temperature increases, so does the saturation vapor pressure by a fair amount. So for example, at 0 degrees, the vapor pressure here is about 6 millibars, where if I go up to 20, it goes up to about 23 millibars or something of that order. So this increases as temperature. Now remember that the saturation vapor pressure is just what we have in that idealized state, where we're right at saturation. So in the atmosphere itself, we will generally be below saturation. So that gives the idea here of how do we quantify this, how moist the atmosphere is. We use a term called relative humidity. Now there are other ways which we can quantify this, but for this talk we're going to talk about relative humidity. Well, what is the relative humidity? The relative humidity is equal to the vapor pressure, that is the actual pressure in the atmosphere that we're concerned with, versus the saturation vapor pressure. Now remember, the saturation vapor pressure only depends on the temperature, so it's sort of an idealized equilibrium state, saturation vapor pressure. So the relative humidity then is the ratio though. So if it becomes saturated, the relative humidity goes up to 100%. They're usually given in terms of percent here. So if, for example, this is 50%, it means that E over E sub S here is 0.5. We multiply it by 100% to get to 50% in that situation. But again, the major important point here is that the saturation vapor pressure increases with temperature, or if we think of the other way, it decreases with temperature. So I'm going to use an example here to show when we cool air that actually the relative humidity goes up. And this is sort of critical to cloud formation, because we're going to find that if we cool the air and we actually get to the point where we're at saturation, we can form a cloud. So let's illustrate this just a little bit more. And I have a few little numbers here, but hopefully that's not too complicated in what we're doing here. But I'm going to start out with air that's at 20 degrees C, and then I'm going to cool that air. And initially it has a relative humidity of 60%. So we make a measurement and we say the relative humidity is 60%, the initial temperature is 20 there. So if I look at 20 degrees C, I can go over to my graph here and I can find the saturation vapor pressure, and we find that that vapor pressure is 23 millibars. So if the relative humidity is 60%, then we can solve for E here, and E is going to be 14 millibars from that calculation. Now if I cool that air at the same level in the atmosphere at least, if we cool that air, then the vapor pressure is going to stay the same, but when I cool the air, the E sub S goes down. So here's the initial temperature at 20 degrees C, and I'm going to cool it down to 15 degrees C just to illustrate the point here. So we are to cool the air down, and when I do that, I get a new E sub S, and that E sub S is now 17 millibars. So now I can recalculate the relative humidity. Relative humidity is equal to 14 over 17. The E didn't change. 14 to 17 is 82%. So in this cooling process, the relative humidity has gone from 60% to 82%. Well, this is critical in the atmosphere. This is one of the ways in which clouds form, sort of the major way in which clouds form, is through this cooling process. So basically we can lift the air. Air cools, and what happens was air is lifted in the atmosphere. As air goes up in the atmosphere, it goes to lower pressure, and that means that the air expands, and that's a cooling. The opposite of that is if we take the air to higher pressure, say we take the air at some level, we bring it down to some level, the air compresses. That compression is a warming process. So we have this expansion of the air as the air ascends. And so if we start out with relatively moist air with a high relative humidity, we can find as the air goes up, it cools. At about 100% then, we should have air which is saturated in this parcel or this volume of air that we're considering. So that's the kind of the idea behind how clouds form. Air lifts, rises, expands, cools, and if the air is moist enough to start with, and we get this expansion and cooling, then we can reach a relative humidity of about 100%. So I'm going to illustrate this process here. I have a bottle here, a closed bottle that we can see here. It has a valve on it, so we can change that. And I put some water in here so that we know that the environment in here is close to being saturated already. So we know that the air right now is close to 100%. So I'm going to try to cool that air down and then see if we can form a cloud. So let me just look at this and make sure the valve is closed. I've got a valve here. I have a pressure gauge and I have a thermometer here. So I'll turn the thermometer on and we'll look at that. And I'll also put a light on here so we can see things a little better. Okay, so there we have our container. There you can see the water. See, we're close to saturation. This is the pressure gauge and this is the thermometer. So as the pressure goes down, this dial will go in this direction, and we can also look at the thermometer. Now, this is basically an inflation pump, which I've reversed so it becomes a vacuum pump, so I can pull air out of the container here. So that is basically lowering the pressure, so it's simulating what happens when an air parcel or a volume of air goes up in the atmosphere. It expands. So this is going to be basically an expansion. I'm going to lower the pressure in here. So if I start out, we can watch this dial. It should go this direction. Let me just note the temperature is 24.2 right now. So that's what the temperature is inside. So if I pull that down, well, we didn't get a cloud, first of all, but we did see the pressure going down, and the temperature has gone down. It's 22.6. So we got some cooling in there. So the question is, why didn't we get a cloud? So that's a good question. Well, it turns out that we're missing one ingredient here. And this same ingredient is at play in all the clouds we see in the atmosphere. And that ingredient is that the water molecules that are in the vapor form, to form a droplet, they have to form it on some kind of a site. So in the atmosphere, that can be form of dust or salt particles or smoke or other types of things. So I'm going to try to simulate that by adding some smoke to here. So I have a little incense stick here, which I'm going to use as a smoke source. We have that. Okay. And you can maybe see the smoke here. Okay, so we have smoke. So the way I'm going to get that into the container is I've already lowered the pressure. So if I open this valve, then the air is going to rush in and the pressure is going to go up. So you'll see the dial go down here. And when I do that, okay, so now I have put some smoke particles in there. So let's see now if this idea is correct, that the clouds need something on the cloud droplets have to form on some type of a nuclei. So now I can close the valve again, and I'm going to pump it down, and immediately a cloud forms. So the secret ingredient there was cloud condensation nuclei. So again, the temperature has gone down, but this time we can see the cloud. And if you look at it closely, you can see the little droplets. And in fact, they're settling a little bit as time goes along here. You can watch, and the top of this will settle. So they do settle slightly, but definitely we've formed a nice little cloud. So that's a good demonstration of how clouds form by this expansion process, or the lifting in the atmosphere. So let me shut the light off here, and then we'll go to the next part of this. So let's see here. So before we said how to form, we talked about the lifting here. So here's the new part of this. We have these small particles called cloud condensation nuclei, CCN. And they serve as sites on which the droplets can form. Now, I just made this cloud here using the smoke, but in the atmosphere there are other different things on which the clouds can form. And some of those are more efficient or more effective in producing cloud droplets. For example, if we have hygroscopic particles like a salt particle, it can get condensation as possible when the relative humidity is below 100%. So we know that the salt is water seeking. If it's a nuclei, it's much more efficient than other nuclei which might be more water repelling. And so there the condensation will occur when we have a relative humidity which is over 100% in that situation. So that's pointing out the role of the cloud condensation nuclei. Going back again, this whole lifting of the moist air was critical for the cooling, but for the droplets to actually form, we needed a nuclei on which they form. So now let's go to a next part of this here, is how clouds form in the atmosphere. And we have to look at what processes there are that cause the cloud to be lifted. So the first one I'm going to talk about is that associated with updrafts in the atmosphere. If we have a situation where the air is coming together, we can actually get an updraft. This is called convergence here. We can updraft that way. Some of these things are called thermals. If a surface gets heated, there can be spots which are warmer than the air adjacent to it. And those spots are like a warm hot air balloon, and they will just rise up. So this is one of the main mechanisms where we get what we call cumulus clouds. So we can see here's a photo of some clouds. And with each of these clouds, there is an updraft that's gone in to make that cloud. Now, if we look at deeper clouds, cumulonimbus clouds, we'll find the same thing. We find that there is an updraft in there. And now, in severe clouds, that updraft can be fairly strong. So that's why if you're flying an aircraft, you usually try to avoid some of these bigger clouds, because the updrafts can be very strong, can be very turbulent in there. And if you've ever flown in the airplanes, a lot of times when you get in the clouds, you do feel turbulence in there, and that's because of this mixing the updrafts and downdrafts that are going on inside the cloud. And I've also shown that, for example, in a hurricane, here you can see the eye of the hurricane, but in the eye wall itself and in the bands around it, these convection bands, the air is rising, and that's giving rise to the actually it helps produce precipitation, which is a major driving force for these systems. So once the clouds form, the precipitation can form. So that's going to be a topic of one of our future talks, is how precipitation forms. That's a different process, but we're going to save that for one of the other lectures here. So this is one mechanism by which clouds can form in the atmosphere, and so this is the type of clouds that we see associated with that. A second mechanism is associated with warm fronts and cold fronts in mid-latitude cyclones. So here's a picture, satellite picture showing this cyclone here. And we have a warm front. We basically have warm air which is overrides cooler air like this. So in that process, it's lifted because it's warm, it's a little less dense, and so it's lifted this way. And that can give rise to clouds here. So where the warm fronts are in this part of this cloud, we can get the clouds to form that way. The cold front, the same idea here. The cold air is pushing this way, and then this warmer air gets pushed up and lifts there. And that can give rise to clouds through this lifting process associated with the cold front. So here's these cold fronts extending out from here, some of the clouds here. Sometimes there's squall lines and other severe weather that forms, which is actually initiated by this kind of a process here on this lifting process. So that's the second way in which the lifting can occur. Another one that occurs in the atmosphere is through what we call orographic lifting. So if we have a flow over a mountain or some kind of a ridge, we find that the air ascends as it comes here, and then it generally comes down again on the other side here as it goes through here. And so the cloud will form here, and as it comes on the other side, actually the air descends, it warms, the relative humidity will get lower, and so the cloud will disappear again. So in this case, the flow is this direction here, over this mountain ridge here. There's just this little ridge here, and so the cloud forms here. And then when it comes down on this side, eventually it dries out, and we don't have a cloud extending all the way down to the surface. We also see these over mountains. These are called lenticular clouds, like a lens. They look like a lens. This happens to be over the Rocky Mountains, and if you have been in the Rockies, you can see that, or you can find many of these good images on the web if you're interested in studying more about those clouds. Now, I'm just going to show one other case here. This one, these clouds are not quite as critical to weather, but they illustrate the idea of lifting. So another way we can get lifting, if we have a cumulus cloud, so say if there's an updraft here in this cumulus cloud, and the airflow is like this, then the flow is perturbed upwards by this rising thermal that comes up here. And so here's a little cloud that tops this. You can see this. So as the air, this is like the mountain cloud in a way. The air is coming up, condenses, and then as it goes down again, it evaporates. And so we see this kind of a cloud. We call the Pileus Cloud is the name for it. Here's another really nice picture of this Pileus Cloud. So those are not as important for climate and weather, but they're nevertheless illustrate the point and the impact of lifting on these cloud formation. So let's kind of summarize here a little bit. So we get cooling of moist air by lifting through thermals, fronts, orographic processes, and that's one of the principal ways in which clouds form. Important to note, though, that we need to have the droplets form on a cloud condensation nuclei. It's very difficult to get a cloud without CCN. Very, very difficult, in fact, almost impossible. It's also very hard to find places in the world where there are no CCN. Even over the open oceans, there still tends to be sea spray and other things. But there are places in the southern hemisphere which is very, very clean. So, the other processes involved, which we are not going to talk about today, but will be the subject of some future talks. One is radiative cooling. So if you're in a valley at night in the summertime, sometimes you can get some cooling. And this is by a radiative process, which we're not going to talk about now, but that cooling of the air near the surface can give you a cloud, which is fog. Fog is just a cloud at the surface. And there's another whole series of clouds that are mixing clouds. These mixing clouds are not really terribly important for weather and climate, so I'm going to not talk about that in this particular talk. So there we have it. So if you're interested in learning more about some of the cloud and teaching tools that we are making available to the public, you can go to the site www.cloudprofsolutions.com or seemyclouds.net will get you there. If you need to write a note, you can write it to me at info@cloudprofsolutions.com. And if you're interested in some of the new videos, they will be posted on this site. Also, if you'd like to do the cloud demonstration, or you'd like to get the equipment to do that, or get the bottle to do that, that is also available in several different forms, ranging in what capabilities you're really looking for here, from sort of the type of bottle that we have here to this larger version here, which is a 5-gallon jug, which is good for demonstrations to a larger group. Comes with a booklet that describes how to make a cloud and gives a little bit of the science behind it.